Bismillahirrahmanirrahim. In our last class, we had seen how to deal with fluctuating stresses. That is, where the mid-range stress, sigma m, does not have a value of 0. So in that case, you have an alternating component of stress, the amplitude component, and you have a non-zero mid-range component of stress. And both of these are achieved by using your fatigue stress concentration factors. You apply these to get these values, and essentially what we do is we plot on this fatigue diagram, we plot these values. This is the mid-range axis, this is the axis for the amplitude component of strength and stress both. So these lines are there. This is the Langer line, yield line, and this is the Modified Goodman line. And for example, if your point plots here, that is, this is your sigma m, this is your sigma a, then graphically you know that it is falling under both the lines, so it is safe as far as yielding as well as fatigue is concerned. So we should expect infinite life for this component. But actually what we do in reality is, instead of plotting it like this and then drawing from the origin, joining this point and then extending it, this is the origin, this is your point x, and where it intersects your Modified Goodman line, let's call it the point G, and where it intersects your Langer line, let's call this L. So if we were to do it graphically, this is the load line. It is nothing but an extension of OX from origin to this point and then extending it. Now graphically, if we were to do this, we would easily be able to calculate our fatigue factor of safety as OG over OX and our yield factor of safety as OL over OX. Now obviously in this region your fatigue should dominate, so because the fatigue factor of safety is less. If on the other hand this point was plotted somewhere around here, then you can it's very obvious to note that in that case these will be reversed. You'll have a bigger fatigue factor of safety than a yield factor of safety, and therefore it means that on this line, if you were to increase your loading, yielding will occur first. But actually what we do is we don't graphically draw this diagram and then plot our point to scale and then measure these distances. Obviously if we do that, you'd get the right answer, but obviously it is better, faster, more accurate to use equations. So let's coin the equations for the Goodman failure line equation, and it is because it's a straight line, it's very easy to see that the equation is SA over SE, we'll talk about this point, plus SM over SUT, because we have two lines, so it's very easy to see, is equal to 1. This is the Modified Goodman line, this is the failure line equation. This is the equation for all the points on this line. If you can satisfy this equation on 2 points, this and this, then it should satisfy all other points because it's a straight line. Let's see if it satisfies 2 points. Let's take point 1, which is an obvious one, this one. On this point 1, you have SA is equal to SE. This is SE. This is the SA axis. And at this point, SM is equal to 0. Because this on the y-axis, SM is 0. So if you put these values, this one becomes 1 plus 0 is equal to 1. So this point 1 satisfies this equation. Now, does this point satisfy the equation? Let's see. In this case, SM is equal to SUT. SM, this is the SM axis. And on this axis, SA is equal to 0. So if you put these values here, this becomes 1. This becomes 0, 1 is equal to 1, so again this is satisfied. So it's very easy to see that this is simply the equation for the Modified Goodman line. Now we also have the Langer line. Let's also see if we can devise an equation for it. It is equally simple to come up with the equation. In fact, it is simpler. In this case, again, we have 2 points and the rest is just a joining of the two. So it's very easy to write an equation for this. In this case, SA, this SA axis, SA over SY plus SM over SY is equal to 1. This is the Langer line equation. Now let's see if this is correct. Again, for this we have this point 1 and now we have this point 2. So point 1 SA is equal to SY, and on this axis obviously SM is equal to 0. You put these values, this becomes 1 plus 0 is equal to 1. So this equation satisfies this point. If it, this point, I'm sorry. Now to this point, on point number 2, your SM is equal to SY this time, and SA is equal to 0. This time if you put these values here, this is 0 plus 1 is equal to 1. So again it is satisfied. So this equation is, we should confidently keep this as a Langer line equation, and this one can more simply be written, because the denominators are the same, like this. Now we have been able to write the equations for the Langer line as well as the Goodman line, but these two equations describe all the points that lie on either of these two lines. But in our case, when we design components, we want our load point to lie beneath, under these two lines, not on these lines, somewhere around here. So we need to be able to plot our sigma A and sigma M values in these equations. So essentially we want, if we have a factor of safety, for example n, we want, I'm just talking about this Goodman line now. If the point plots here, this is the line which will run parallel to this Modified Goodman line if we keep a factor of safety of n between this point and this one. Because if this point x lies on this point or anywhere on this line, then you have factor of safety of 1. We want the factor of safety to be more than 1, so we are just going to use, instead of SA, we will use n sigma A. Whatever our stress is, we multiply with n, and then it comes to this point. Similarly, SM, we multiply this with these are the coordinates which we should plot on these equations if we are talking about the stress values and not the strength values. So if the next what remains is simply putting these values, instead of SA and SM, we are going to use n sigma and n sigma. The difference between sigma and S, of course, being S represents strengths while sigma represents the stress values that are occurring. So if we simply replace these SA by, if I'm talking about Goodman design equation, because we are going to figure out if there is a factor of safety there or not, what sort of factor of safety is there. So we have just replaced this n sigma A over SE plus n sigma M over SUT is equal to 1. This is the shape that the Goodman line takes, and it's very here I'll just use this subscript F for factor of safety, because we have two factors of safety, one for yield and one for fatigue. So we are talking about fatigue here, so I use this subscript F, and if I rewrite this equation again, this is our design equation for factor of safety incorporated. This one, the original equation, this was for this line. This one is for any line that passes parallel to this. It could be upwards also, it could be on the other side also, and in that case you'll have a factor of safety less than 1. We want this to be more than 1, but we don't want our point to be plotted on this line. We want it to be plotted somewhere below this line, parallel to this line, somewhere below it. So we replace this S by n sigma, and this is the equation that basically gives us the value of factor of safety for fatigue. Now if we take the other equation, Langer design equation, because in design we don't desire our point to land just precisely on this line or on this line. We want it to be below these lines. So again we want to incorporate a factor of safety here. In this case again we replace SA by n sigma a and SM by n sigma m, and again here we will use a subscript of y for yielding. I'm going to, this is easier, simpler equation, so I'm basically using this equation. And simplifying this, you get, this is your design equation for line. So instead of plotting our points, graphically drawing this, plotting our point, and then measuring these things, we are just going to use the same quantities but in these equations to find out whether our design is safe or not. By safety I mean both of these should be more than 1. NF and NY should be more than 1. It could be less than 1. It means this point will be plotted on the other side of these lines, so that will be a factor of safety less than 1. But if it is below these lines, it will be a parallel line in this case, and if you talk about this, then you have another line which is again parallel to, because this is your point which is plotted, so again parallel to this you will have, and this is the factor of safety, this divided by this, and in this case this divided by this. So this is how you basically solve your problems, and we are going to demonstrate that by doing a problem, a numerical problem, and let's see how this principle translates into practice. This is your problem statement. This is from your textbook, but this is adapted from problem 626, slightly changed, but essentially it's the same thing. And this is an axial loading problem. You have seen this type of problem before, but in that case it was a fully reversed case. Here we have an alternate, a fluctuating case, because the load varies from 12 kilonewton to 28 kilonewton. Otherwise this is pretty much the same problem. There's another complication as well, and that is the question asks you to find out the fatigue factor of safety based on achieving infinite life. That is easy, we have seen that, we are going to do it. And the yielding factor of safety, we've also seen that. But the final line, if infinite life is not predicted, let's say your factor of safety comes out to be less than 1, which will mean that there's no infinite life, then estimate the number of cycles to failure. So this is another part of this problem which we have discussed in the previous problem, but we are going to go into more detail here. So let's start with this problem, and this is AISI 1040 steel CD is Coltron. If you go to the back of your book, you'll find out that for this material you have SUT is equal to 590 MPa and SY is equal to 490 MPa. simply read it from the appendix at the back. Now you have been given axial fluctuating load, and this load is something like this. If I draw it graphically here, it's something like 28 kilonewton, 12 kilonewton. Now this is F, obviously. This is F max. This is F min. But because it's an axial problem, if you divide this by area, your stress situation will also be something like this. We don't know the number yet, but you'll have a sigma max and you'll have a sigma min. Values we are going to find out presently, but the main thing being sigma mid-range will not be equal to 0, and because it will not be equal to 0, unlike the last question which you did where the fluctuating load was from I guess minus 28 to plus 28, or whatever the values were, they were equal, positive and negative. So in that case you didn't need to draw the fatigue diagram. SN diagram was enough. Here you need to do that. Now let's find out the loading situation. F mean, F max plus F min over 2. Now you may be familiar with another form of this. Sigma mean is equal to sigma max plus sigma min over 2, and similarly sigma, this is the amplitude component, sigma max minus sigma min over 2. But the equally valid expressions are force expressions, and if you get Fm and Fa first and then divide by the areas, you'll again get these, so it's the same thing. Fm turns out to be 28 plus 12 over 2 is equal to 20 kilonewton, and similar expression, minus F min over 2 is equal to 28 minus 12 over 2, 16 over 2, 8 kilonewton. This is your Fm and Fa values. Now for calculation of stresses, because we are dealing with stresses first, let's call about stresses first. We'll talk about strength later on. Now the next thing is, we have just discussed that in this problem we need to have the fatigue factor of safety, the fatigue stress concentration factor included. This is a fatigue problem. You just cannot take stress concentration factor to be 1 anymore here. So Kf is needed. Now this Kf obviously is a function of two things. Kf is equal to 1 plus Q Kt minus 1. Now Kt is a geometric stress, is the geometric stress concentration factor, and it can be read from table A15(1), because d over w, we know d over w is this divided by this diameter of this hole divided by this width. So this is basically 6 over 25, which is 0.24. So reading against d over w of 0.24 from the chart, you can easily read that Kt is equal to 2.44, nearly equal to 2.44, because it's not very easy to read it accurately. Now what about Q, Naught sensitivity? Q can be, because it's a normal stress situation, it can be read from figure 620, and 620 basically asks you about the radius, which is in this case radius of this hole, which is 6 divided by 2, 3 millimeters. And you also need to know the material, and SUT for this we already know is 590 MPa. So for these two values, you can again read that Q is roundabout equal to 0.83. Putting the values, Kf is equal to 1 plus 0.83 kT minus 1, 2.44 minus 1. This turns out to be 2.20. This is the Kf. This is the fatigue stress concentration factor that we need to apply to our stresses. Now we have this FA and FM values. Now we also have Kf value. So let's find our mid-range stress and our alternating component stress. These are Kf. We have to multiply both with Kf because we are talking about fatigue problem. And the rest is very easy. This is F m over A. This is F, the axial problem, Fa over A. Putting the values 2.2 into Fm was 20 and Fa was 8. 20 to 10 raised to power 3 because it's in kilonewtons, and the area is again simply we are going to deal with this cross-sectional area. So you have to subtract 6 from 25. So 10 millimeter is the thickness. 10 into 25 minus 6. Similarly, here you have into 20. Here you have the value for alternating component was 8 into 10 raised to power 3 over 10, 25 minus 6, and this is 231.58 MPa, and this turns out to be 92.63 MPa. Not so much for the stress values. When it comes to strength, you know that endurance limit is simply half of the SUT. So 0.5 into 590, this is 295 MPa. Now, we don't need to find out the SE value, and that is Ka, all the factors, marine factors, Kc, Kd, Ke, Kf into Se prime. Now Ka, surface factor, we are told that it's a cold drawn component. So for cold drawn, if we consult table 6.2 for cold drawn, you have the equation for Ka is very familiar one for you, and the values of A and B from table 6.2. A is 4.51, whereas B is equal to minus 0.265. So putting these values, Ka is equal to 4.51 into SUT, we have 590 minus 0.265, and Ka then comes out to be 0.832. Now what about the other marine factors? Kb is the size factor. You just make it equal to 1 because it's axial loading, and in axial loading you simply use one value, and this is equation 621. And why we make it equal to 1 is because we have to go to Kc anyway. Kc is the loading, the load factor, and Kc for this case is 0.85 because it's axial loading. So we don't bother with this, we just go to Kc, which is 0.85 for this case. As far as Kd, Ke, Kf are concerned, you don't need to worry about those because There's KD's temperature, this is reliability, this is miscellaneous, nothing is mentioned, so you don't need to consider those things, any of those. So your SE turns out to be then equal to 0.832 into 0.85 into SE prime 295, and that is 208.62. This is the value of SE. Now you have to the next step is simply using your uh, equations. This is your equation for the, because we have been asked to use the modified Goodman criterion. So this is the equation that we are going to use. We have all the other quantities in hand. So sigma A over SE plus sigma M over SUT is equal to 1 over NF. Sigma A is equal to 92.63 over 208.62 plus sigma M 231.58 over SUT is equal to 591 over NF, and NF turns out to be 1.20. So therefore there is infinite life with a factor of safety in fatigue of 1.2. Now we also have another mode of failure, that is the yield failure. So again, putting the values in this equation, this is your modified Goodman criterion. And now when we talk about the Langer line, I'm sorry, sigma A plus sigma M is equal to SY over NY. Again, this, and the Y means, this denotes the yield factor of safety. So putting the values here, sigma A plus sigma M, you have 231.58 plus 92.63 is equal to 490. Remember, this is the value of the yield strength of the material, and NY turns out to be 1.51. Now this equation, this is, we are checking basically yield, and here we were checking fatigue. It's good practice to check both, even if the question doesn't require you to. So we can simply, if we talk about where this point plots, obviously we did it analytically, but graphically speaking, because your fatigue factor of safety is 1.2, whereas your yield factor of safety is 1.51, this is not plotting anywhere here. This is plotting somewhere around here. So if you extend this point, if you increase the loading proportionally, then first it will cross the fatigue line and then the Langer line. First it cross the modified Goodman line, and so this plots here. Otherwise, if the yield factor of safety was less than the fatigue factor of safety, it would have plotted somewhere around here. We don't worry about these things because numbers tell us everything. But now we have to come back to one part of this problem that we haven't done yet, and that is, obviously the fatigue factor of safety is more than 1, so our question is complete here. But there's another part of the question. If infinite life is not predicted, estimate the number of cycles to failure. Now here infinite life is predicted, but what if infinite life was not predicted? What would have happened then? Then what would have happened is this. We're going to forget about the Langer line in this case. Langer line has nothing to do with infinite life or number of cycles. If this was your modified Goodman line, this is modified Goodman line, and if you recall, this point is SUT. This point is SE. If your factor of safety in fatigue was, which is actually 1.2 in this case, it was less than 1 point something, then it means that there would have been no infinite life and your point would have been plotted here, somewhere above this line. Now, we have discussed this in our last lecture, that in this case, if it was the case and it had been plotted here, what should we have done? We have discussed this earlier, and there we just talked about starting from this point, extending it, this line, passing through this, and then touching the y-axis, and this gives us basically sigma completely reversed. Now, why is this completely reversed? Because on this line, on this y-axis, sigma m is equal to 0. So this sigma is basically, this sigma, whatever this value is, this is equivalent, completely reversed stress. Why equivalent? This question is not a completely reversed question. This question, if it's plot somewhere here, there's a sigma m and there's a sigma a. So this is not a complete reverse. But when you extend this point to this point, this is equivalent completely reversed stress with the same fatigue damage as this. This means this current fluctuating case. And how to find this sigma rev, sigma completely reversed? Again, we don't plot it to scale and then measure these things. We have the equation for this modified Goodman line, and if you recall this equation, the modified Goodman line is simply sigma a over se plus sigma m over sut is equal to 1. This is the, and we are not going to use factor of safety here because now we are talking about this line, okay? But now in this case, the point is not even on this line, the point is on this line. So we simply replace SE by sigma rev. And if we rearrange this, sigma A over sigma is equal to 1 minus sigma M over SUT, and sigma completely reversed then turns out to be sigma A over 1 minus sigma M over SUT. And one thing that you can be sure of is this will be greater than SE. This will be greater than SE, obviously, because SC is this. If it had been, if the factor of safety was 1, it would have plotted somewhere along this line. Then this equation would have given you SE. It is factor of safety if it was less than 1, then it will give you a stress that is higher than the SE. And obviously it is higher, that is why there is no infinite life. If it was SE or lower, then there would be infinite life. So now what we should do with this sigma ref in this case, very simple, go back to your SN diagram. And we have discussed this part. This is your SN diagram. This is your SE, and this region, this is the finite life region. So your sigma rev will be greater than SE somewhere here, whatever the value is. We just plot it, and this is very easy to plot, you know. And then this is your number of cycles. And how to calculate the number of cycles? It's again, we have done it. Once you have this value, sigma rev, then it's very easy to calculate n, because in this region, finite life region, for finite life region, we have this equation, SF is equal to A and B. You know how to use this. If you know the value of n, you can find the fatigue life. by using A and B, and A and B can easily be found out. You can, if you know the values of SUT and all that sort of thing, you can calculate these things. But here we want to find out N, not SF. For SF, replace by sigma ref. This is sigma ref A and B, and so number of cycles will be simply this. We don't need to use this equation for this question because your NF was greater than 1, but if it was less than 1, this will do it nicely. This is another example problem. This is adapted from problem 629 of your textbook, and it reads, on the latching spring shown, this is a latching spring, a preload is obtained during assembly by shimming under the bolts to obtain an estimated initial deflection of 2 millimeters. What this means is actually this: you apply some shims here and then you tighten the bolts. Because the shims are predominantly in this region, what happens is there is a this spring takes this dotted shape because of these shims. Obtain an estimated initial deflection of 2 meters. Then what happens is you apply a force here, and then that force brings the spring to an even keel like this shown. So this is a what is called preload. Okay, this is F preload, and that is what is talking about here. To obtain an estimated initial deflection of 2 millimeters, the latching operation itself requires an additional deflection of exactly 4 millimeters. So this is the starting position now after the preload application, and then the latching operation requires another 4 millimeter deflection. So there is a preload which is responsible for 2 millimeter deflection, and then there is a further 6 millimeter. So the total force at this point will be corresponding to a 6 millimeter deflection. The material is ground high carbon steel, bent, then hardened and tempered to a minimum hardness of 490 Brinell. If you know the Brinell hardness number, it's rather easy to calculate the SUT, so no problem there. Estimate the yield strength to be 90% of the ultimate strength. If you know the ultimate strength, then it's very easy to find the yield strength because it's given. Now, determine the maximum minimum latching forces. We know the maximum minimum deflections, 2 and 6 millimeters, but what are the forces corresponding to these deflections? That is part A. Part B, the fatigue factor of safety for infinite life using the modified Goodman criteria. Now, this is mentioned that you may use a fatigue stress concentration factor of 1.5, which includes the effects of curvature and Naught sensitivity. Now, luckily we have this, so we don't need to go into the curved beam analysis because this is actually a curved beam, and the simple beam analysis won't give you the correct answers for this. But since we are allowed to use a fatigue factor of safety of 1.5 here, because the maximum stresses will be somewhere around here, we can dispense with that rather complicated analysis, although it's not that difficult. If you want to do the curved beam analysis and you don't want to use this, then you can go to section 318 of your textbook, and you'll need the internal radius, this inner radius, outer radius, and then you can calculate more accurately. But since this is not a lecture on curved beam, so we should focus on the fatigue part of it, so we are just going to use this concession that is given to us. Let's start this problem. The rest is rather easy. First we deal with the first part of the problem, which is very simple, and that is the maximum minimum deflection forces. We know the displacements, only we don't know the forces. So let's start. For cantilever beams, the deflection, which is a very well-known expression, and even if you don't remember it, you can find it from table A9 from the back of the book. So, but most engineers know this by heart. Now this negative sign is just for the downward direction. So as far as magnitude is concerned, this is it. So if you rearrange this, we want to find the force. We have the deflection, we want to find the force. So F is basically 3EIY over L cube. Now this is material constant. Y we know, we have two values of y, and as far as I is concerned, I for a rectangular section is BH cube over 12, and that is B is 20, H is 4, 20 into 4 over 12, and this is 106.67. Now F min, the preload part, that is simply 3 into E 200 GPa, so we just write it in MPa. So this is for steel 200 is the Young modulus, then I 106.67 is just calculated, and then the preload deflection is simply 2 millimeter. It's 2 over length is 140 millimeter length of the cantilever, and this is 46.65 Newton. F max, again use the same expression, only for y instead of 2 there should be now 6, because the total deflection 2 was just the preload, then the latching operation required another 4 millimeters, so the total is 6 now. Yes, obviously we can do it the correct way also, and 106.67 into 6 over 140, but no need to calculate this because just it should be 3 times this one, so this is 139.95 newtons. This is as far as the first part A is concerned. Part A is finished. These are the latching forces required. Maximum and min. This is the minimum latching force, this is the maximum latching force. Now we proceed to the B part, and B concerns fatigue factor of safety for infinite life using the modified Goodman criterion. So we again go through the same process we just did for the other problem, and that being, first we calculate the mid-range force. Again we are going to calculate the mid-range forces and the alternating component force, and then use the formula to calculate the sigma A and sigma M, just like we did in the last problem. Max plus F min over 2, and this is 139.95 plus 46.65 over 2 is equal to, this turns out to be 93.9 newtons, 93.3 newtons. F max minus F min over 2, this is 139.95 minus 46.65 over 2, this is 46.65 newtons. So this is FA and FM calculated. Now we move on to the stress part. Now sigma A is nothing but KF. This is fatigue factor of safety, you have to use this, and we have been given this value 1.5. MAC over I. This is the formula, flexural stresses, and this A signifies this alternating component, amplitude component. So this is 1.5 into FA 46.65. So the maximum moment happens around here, this force multiplied by this distance 140. So somewhere around here you have the maximum stresses. So for 46.65 0.65 into 140. This is your M. What about C? The section is 4 millimeter. So if you're talking about this neutral axis, then you're talking about 2 millimeter down and 2 millimeter up. This is the maximum stress. So use the value of 2 into 2 over I. We have just calculated 106.67, and this is sigma A. It turns out to be 183.68 MPa. Sigma M, similarly, Kf M, mean mid-range component of moment, C over I. Here again, the only thing that changes is this. Instead of MA, we have MM. MM is now 93.3 into 140. The moment arm is the same. This is now MM. 2 again, distance from the neutral axis to the outer fibers, over, similarly you have the same moment of inertia, and this turns out to be 367.36 MPa. So this is the stress part. Right from the start, there's a comparison of stress and strength. So we have these stress values in place. Now we deal with the strength values. Now we have been given the value hardness, Brenner hardness number values, and that is 490. Refer to the question statement. Brenner hardness number of 490. Now we have a very useful expression for SUT, which is nearly equal to 3.4 into the Brenner hardness number. Now 3.4 multiplied by 490, that has been given. This gives us 1666 MPa. Now the question statement also says that the yield strength can be taken as 90% of the ultimate strength. So we have the ultimate strength here. So SY then turns out to be 0.9 into 1666, or this is SUT. So SUT value is equal to 1499.4 MPa. This is your material properties. Now once you have SUT and SY, the rest is easy. SE prime is basically 0.5 into SUT, but this is if for SUT less than or equal to 1400 MPa. For SUT greater than 1400 MPa, which is the case here, this one is greater than, then you simply have SE prime is equal to simply 700 MPa. It's a constant value. You should recall this from our initial lectures. So SE prime is there. Now SE is simply KA, KB. Again, repetition we have done so many times. KD, KE, KF into SE prime. Now KA is equal to ASUTB. This is the surface finish, and because it is ground, let's refer to the ground high carbon steel. So you will refer to table 6.2, and for ground components you have A is equal to 1.58 and B is equal to minus 0.085. Putting the values 1.58 into KA is this. For KB is the size. This one is surface, just a reminder, KB is the size factor. For KB, one needs an equivalent diameter. Why? Because it's a bending problem, but it's not a rotating bending problem. So you need an equivalent diameter. An equivalent diameter for rectangular sections, you can refer to table 6.3, and that is simply 0.808, and we have done this too before. HP 0.808 into 20 into 4, these are the cross-sectional dimensions, and this turns out to be 7.23 millimeter. Now this is slightly less than the rotating beam experiment specimen diameter, which is 7.62. So you should expect this size factor to be greater than 1, because this is less than 1. Remember the statistics of cracks. So once we have this equivalent diameter, now we can put this D in our equation for size factor. This is the equation, and put the value you just calculated, 7.62, and this turns out to be nearly 1, but slightly greater than 1. Now KC, load factor, this is bending, so this is 1, nothing to worry about. And as far as KD, temperature, no mention of any temperature, no reliability discussion, no miscellaneous things. So we are justified in taking all of these as 1. So we can simply take KD, KE, KF is equal to 1, because the question tells us nothing about that. So at SE simply turns out to be 0.841 into 1.006 into SE prime, which is 700, and that is 592.2 MPa. So now we have the strength part also covered. Stress we had already calculated, stress values. So the strength part being covered, now what remains is simply to plug in the values. And again, this will be a repetition as we have done this earlier. So first of all, fatigue. Let's check fatigue by the modified Goodman line, and we know the equation sigma A over SE plus sigma M over SUT is equal to 1 over NF, fatigue factor of safety. And let's take the values of strength and stress. Sigma A 183.68, sigma M 367.36, and we have just calculated SE 592.2, and SUT is 1666. So all these values are now known to us. So putting in these values, 183.68 over 592.24 plus 376.36 over 1666, yes, that's correct, is equal to 1 over NF, and NF, fatigue factor of safety, turns out to be 1.87. Now this question does not specifically ask us to calculate the yield factor of safety, but it's good practice to always check that. And for that we'll again refer to the fatigue equation, the Wenger line equation, which incorporates the factor of safety, sigma A plus sigma M over Sy over Ny. For yield check, sigma A plus sigma M over Sy over My. Sigma A, sigma M values we have just used, using them here again, 376.36. Sy value we just saw that it was 90% of the yield strength, 90% of the ultimate tensile strength, and that turned out to be 1499.4 MP. 90% of the yield strength, 1499.4. And NY turns out to be 2.68. Again, this can be plotted just for understanding sake. We don't need the plot to calculate anything. This was the modified Goodman line, and this is the, again, the factor of safety for fatigue is less than the factor of safety for yield. So it will plot somewhere along this region, not here, somewhere along this region. And obviously the stresses also indicate that, but somewhere along this point. So that this is the load line, this is the Langer line, this is the modified Goodman line, and the point plots below both of these lines, so there is no danger of fatigue as well as yield. So the design is safe from both points of view. Thank you.